Okay, everybody can see the slides okay? It all
Yes.
came up and you can hear me. Good. Okay, so I'll start with my introduction. I'm Chris Kontoes and I work at Delmar Oceanographic. I've been an ocean technician for over a decade and worked at a couple different companies, including like Nortec and RBR, kind of doing sensors. And moving from sensors into platforms has been a really fun thing because I actually, through both of those previous companies, I sold instruments to Delmar Oceanographic, and that's kind of how I ended up here. It's been a really fun journey actually. So I'm going to try to squeeze everything into about 20 minutes because that's the time limit that I was told, right?
It's definitely not hard and fast.
Not hard and fast.
We usually like to pepper people with questions too, which tends to make them go over. So
okay, so I'll try to keep my part to 20 minutes. I'll do my best. But the Wirewalker is what I'm going to go over and just kind of give you a brief introduction of what it is, why we use it, how it works, kind of all that sort of stuff, and why it's an interest to ocean observers. But really, it's super flexible. So like no matter what, there's no way I can cover everything. And so I think it was Chris mentioned sewage, Dan mentioned wind farms, Ray mentioned defense, and Matt talked about other profiling options. So, if I tried to cover all of those things, then I'd be a little bit out of time. But that said, hopefully you'll see that it does work for all those applications. Delmar Oceanographic is a company based in San Diego. We're here in California, where the weather's been super amazing and the surf's been excellent lately, so I can't complain. We've got deep roots at Scripps, and the instrument was actually born kind of at Scripps Institution of Oceanography. And because of that, we're really highly involved in academia, but monitoring and commercial applications and even naval applications are becoming more and more common. Like I said, the flagship product of DMO is the Wirewalker, and it's a rapid vertical profiling system that's powered by ocean waves. The Wirewalker is 100% mechanical. It doesn't require any batteries or power for propulsion. It's all wave powered to move it around. So as you can see in this little cartoon, the system utilizes a surface buoy, which is going to naturally bounce around with the waves. And the buoy is pretty small. It's about 1 meter in diameter. There's a well through the center that's used that you could put like instruments that are going to send things out to real-time telemetry, stuff like that. You could also use it with like a GPS beacon or a flasher and add all that stuff to the buoy as well. But the buoy has really been designed to capture a big range of wave conditions. And it's really proven effective from just like a few centimeters of short period wind chop to really long period swells and big storms. And we typically recommend using our buoy to start off, but there have been a lot of other deployments, kind of customized deployments where they've used bigger instrumentated buoys. Ours is kind of a small buoy that's easy to handle. Underneath the buoy is a profiling wire, and that's held taut by a weight. And the length of the wire is really what determines the profiling depth. And we use an insulated wire rope or a jacketed wire rope so that we could also use inductive modems so that any point along the wire, data can be sent up to the surface buoy. The wire comes in 2 different types of flavors, if you will. There's like one that's for autonomous use that's a little bit more economical. And then there's a real-time one that has a special termination called a hammerhead, which makes the connection to the buoy a lot more robust. And then, like I said, the down weight keeps things vertically taut. You can kind of imagine the buoy on the surface and the weights pulling the wire, keeping it vertical. The down weight kind of keeps the system bouncing with each wave that goes by. Right? So every wave that passes, that whole system is going to bounce up and down. The down weight is not an anchor. So I want to make that clear while we're talking about how it works. It's not an anchor. It's suspended under the buoy. So it's not hitting the bottom or anything like that. And then the profiler is the final kind of basic component of what I'd call the Wirewalker basic system. The two-way motion of the wire It kind of bounces up and down, right? That whole system's bouncing. That two-way motion propels the Wirewalker downward through the use of a one-way cam mechanism, and it eventually hits that turnaround bumper at the bottom where it will float up under its own buoyancy towards the surface. The cam's disengaged, it's completely decoupled from the wire. And so it's a nice, quiet, smooth ascent up to the surface. And that happens at about 0.5 meters per second, is what that ascent rate is. That's what we usually like to have the system positively ballasted to. So this picture here is what an actual photo of a complete Wirewalker system looks like. These are like the real components that we would ship out. So again, it's 100% mechanical. You know, as of right now, I haven't talked about any sensors or anything like that. There's no batteries, and it's just using that motion of the surface waves to move around. And surprisingly, it doesn't really need much. Like I said, it's just a few centimeters of wind chop. The thing will start going pretty nicely. So another kind of key feature to the Wirewalker is that it's customizable. And so we can build it modular so that you can start putting your own sensors in or putting other sensors on or taking things off. And since DMO is sensor agnostic, we're happy to pretty much integrate whatever sensors you have in mind. You know, of course, there's some sensors that are more appropriate for rapid profiling than others. Like you wouldn't want to put something on there that takes, you know, 2 minutes as a equilibrium time. So just real quick, this photo is kind of cool because there's a bunch of different sensors on here. So as an example, this is a group in Hawaii, by the way. That's why they have lays on. But the transmissometer is the big sensor there. And then there's a dissolved oxygen sensor, another sensor that's a triplet. So this one has chlorophyll, CDOM, and turbidity. And then there's a PAR sensor for light measurements. And then you can kind of see it, the little red sensor there. That's an RBR CTD for salinity, temperature, and depth measurements. And then here's a few more configurations and sensors that we've seen work really well. The picture in the middle shows a variety of optical and fluorescent sensors, as well as a turbulent microstructure profiler. And then that's the microwriter there, big, tall one. And then on the left is a plankton camera with a CTD, DO, and some fluorescent sensors. And then the one on the right is pretty interesting, and this has been a cool new advancement. It shows an ADCP, so that one down here shows an ADCP that really it's by putting a high frequency ADCP on the Wirewalker, you can get really fine resolution of currents over a really long range. And by that, what I mean is we've seen about 2 meter resolution doing like LADCP type processing. We've seen about 2 meter resolution over hundreds of meters of range. Typically the black housing here is rated to 300 meters, but they also have a titanium version, so we could actually profile even deeper than that, and you'd still get the same resolution. So as I mentioned, there's a video I wanted to play. This one is really cool. It was created by some Wirewalker users that were on a cruise together, and Melissa is at URI, and Colleen is at the Moss Landing Marine Lab, and they just put together this little stop motion video. So I kind of wish it had like sound or something to it, but anyways, I'll just play it and kind of talk through it a little bit. But you know, again, you can see the down weight pulling that wire taut. You put the Wirewalker on the wire, put various sensors, configure it how you want it, and you deploy it. And then the waves do all the work. It forces the profiler to go deeper and deeper until finally it gets down into the depths, and it'll hit the bumper on the bottom. And then the cam is disengaged. It allows the profiler to ascend smoothly under its own buoyancy, totally decoupled from the wire's motion until it hits the bumper on the top. And then the cycle repeats. So this is my favorite video to play. I think I play it in every single presentation, and I've got it playing all the time. I show it all to tons of people. Should probably pay them at some point. Now, up to this point, the basic Wirewalker system can be used as just a drifting buoy, right? So that's what's shown here. It's just a drifting open ocean type deployment. This particular one has a nice curvature to that plot. You can see here. That was because it was dropped off in an eddy, so it kind of followed the currents around. And then these plots are temperature, salinity, and chlorophyll. And they're from about a 2-week deployment that collected 2,400 profiles and were profiling down to 100 meters. So I like these plots because it's a really cool example of how like dynamic this chlorophyll maximum can be in the water column over time. Now that said, the Wirewalker does work just as well when it's tethered or moored to the bottom. And so these cartoons come from our Wirewalker mooring design tech note, which shows some concepts for simple like shallow water moorings, as well as a little bit more complicated or traditional oceanographic style mooring on the right. Obviously, you know, like Ryan mentioned, DSA has Proteus DS, which can model these things and show you how well your mooring is designed and all that. And so for some of the more complicated ones, it really is necessary, and it's awesome to do. We've had some really cool moored deployments recently in like thousands of meters deep water. And the dynamics are much different than when you're, say, in like 70 meters of water. Here's another plot. Chris, again, I think you mentioned sewage. So this one was actually the Orange County Sanitation, or no, the Los Angeles County Sanitation District using a Wirewalker near an outfall here in Southern California. And the top plot, it shows that it was only at 20 meters deep. So it's actually pretty shallow. And it was deployed for only about a month. But what you're seeing is 18,000 profiles collected. And then the two lower panels marked A and B are zoomed in, showing an 8-hour section and a 4-hour section of this little circled spot here. And so, you know, whether you're free drifting or moored, you can collect a lot of data and get a lot of great resolution with the Wirewalker. And none of it consumes any power for the vehicle motion itself. And so the key here is that you're getting high resolution water column data, both vertically, because you know you're moving upwards and down through the water column quite quickly, as well as in time. And so you know you get a nice, actual, accurate view of the water column. And then you could put various sensors on here. We put the turbulent sensor on, you know, stuff like that, because it's a nice, smooth, quiet ascent. But again, I'd like to get into a little bit about more like why this was produced. So before I get there, I'm just going to mention a few of the applications, which is really hard to kind of talk about because there's so many. It depends on the sensors that you're putting on it. And so depending on which sensors you put on it, you might have 1 or 2 of these applications covered, or you might have another sensor that we haven't used yet, so we don't have the application up here. So this is a really incomplete list of applications, is basically what I'm trying to say. So why do we do this? Why do we like to profile through the water column? Why is the Wirewalker built? You know, why was it designed? And so to demonstrate this, I'm going to talk about what has historically been done through the using like a traditional subsurface type mooring. And so here's a little cartoon mooring that's, you know, attached to the bottom, stretches nearly up to the surface. And then, you know, typically a mooring like this is going to have a bunch of sensors on it. So we'll stick all our sensors on the mooring. And for this particular example, I want to talk about temperature because it's kind of easy to understand and easy to talk about. So we're going to say that these are CTDs on this sensor. I mean, on this mooring. And, you know, the other kind of complicated thing about a subsurface mooring like this is it could be pretty difficult to get real time from. You know, so I'll cover a little bit about that as well. Now, if we had a mooring like this and the ocean was homogeneous, this would pretty much be all you need. In fact, you'd probably only need one sensor because it's kind of all mixed and doing the same thing. So the ocean is obviously not like this. It's not static. It typically looks, something more like this. This is what I'd call a quasi-realistic ocean. There's warmer water on the top. It's stratified down, colder water on the bottom. And, as we've indicated here, it's not just the ocean surface that's moving up and down, but there's also density interfaces, or like internal waves between warm, less dense, and colder, more dense layers of water that also move up and down. So it can get quite complicated. So now we've got a mooring that's measuring temperature at all these different locations, like fixed locations. And over time, as these interfaces are moving up and down, these sensors at fixed locations start to sample these different water layers, or water at different temperatures. But if we looked at the real data, your data would probably look more like this. And so if you squint enough, you might actually be able to see, okay, there's some layering going on here, and it looks like maybe there's some internal waves, something like that. And with a traditional mooring, the vertical resolution is not going to be super defined unless you have a ton of money and you can put a ton of different sensors along that. But if I introduce an even more realistic vertical stratification in our water column, you might end up with data that looks something like this. And so now you're really only using two of those sensors, in this example anyways, to show that there's some variation in the water. The lower, there's like a warm layer on the top, cool layer on the bottom, and then maybe like a thermocline in the middle. Again, squint, you can kind of see these internal waves coming up and down, but it's pretty coarse. Now, from that data, would you be able to tell that that's more like what the real ocean was looking like? So when we want to understand the physical variability that's causing the ocean to change in time, how do we really acquire enough data to interpret this picture here? Do we need to guess where to, congregate sensors? Or what happens if the thermocline deepens or gets shallower depending on the time of year, anything like that? It could be really tough to use these fixed sensors to get the resolution if you're really trying to look at these fine scale variabilities. But even with this, the depiction of our water column is oversimplified. And so the actual ocean is actually really complicated in the vertical, in space and in time. And so it might look something more like this weird depiction where the top and the bottom of the thermocline might each be doing something different. And so now you try to interpret the data from each one of these sensors, things would even get like more confusing. In this case, you might have the upper sensor showing warming that's out of phase with the lower sensors, and the second sensor from the top might not show any change at all. And the point really being that there's some like unified dynamic in the ocean that's kind of moving around all the time in all directions. And it can get extremely complicated. And so again, if we look at what we get from a sensor array like these on a mooring and a water column that looks like that, your data might look something like this. And so if it did, would you really be able to accurately interpret what's going on in the water column? That's kind of why the Wirewalker was made, is to solve this issue. And so if we add even one more sensor to it, maybe we're going to measure chlorophyll as well. And it has the same sort of vertical structure that we were just looking at. We, unless you have a ton of money, you probably are even ending up with fewer sensors. And so your resolution is getting even more coarse. And so again, if we look back to what could be actually happening in the water column, it could be very complicated. We saw this in the drifting plot that I showed. The chlorophyll is distributed, in thick and thin layers, and it goes up and down through time, and it's moving around a lot. And so how do we interpret this, right? How do we get this type of an image that looks like this picture rather than those coarse ones that we're looking at? And so that's where the Wirewalker comes in, why it was invented. And again, it uses the wave motion to go up and down through the water column, and it does it rapidly. And with fast sampling sensors, you get really high resolution. And so you end up like really imaging the water. And that's what I mean by an actual accurate view of the water column. We're essentially stepping through time with rapid profiles. And so again, if we add the chlorophyll sensor here, a little fluorometer, you know, obviously does the same thing. And we can also see that in other types of parameters that you might want to measure. Skip some of this for the sake of time. This is actually a really cool picture. This is like a green tide off of Scripps Pier. But this, I'm going to show another data plot, and it was taken nearby Scripps Pier, kind of in this area where there's a lot of really cool stuff that happens in the canyon nearby. And so kind of southwestish of that pier in that picture is La Jolla Canyon. And a Wirewalker is deployed in about 100 meters of water. And then in these three plots, it's only 9 days shown, but the total record of that deployment was 370 days. The plot on the top is temperature, salinity in the middle, and then chlorophyll on the bottom. Again, the chlorophyll, you can see it thickening and thinning over time, going up and down through the water column. But I really want to focus on salinity right here. And so, you know, take a look at the plot and look at the darker purple band that's kind of goes up and down in the water column. Now check out the color bar for what that is. It's kind of strange. It's actually a layer of low salinity water that's trapped between layers of high salinity. And you can notice that it changes with time, right? It gets thicker and thinner, but it's ultimately very dynamic in time. And so this would be incredibly difficult to measure with even a super well instrumentated traditional type mooring. But obviously I'm showing you this plot because it was Wirewalker data, and so you can see how it really does image what's happening under the water. And then final plot, this is actually from the same deployment, plotted a little bit different, but this time we're looking at individual upcasts only, which the downcast, like you saw in the little animations, it kind of steps downward and then it comes up smoothly. So the upcasts are what most people are most interested in. So this is upcasts only, and each raw sample is represented by a colored dot that's small enough not to overlap with the profile before it, so you actually see little vertical bands if your resolution on your screen's good enough. And then the left-hand plot is temperature, the right-hand plot is backscatter. And basically what we're looking at is 12 hours in each little square, 12 hours of data over a 100-meter profile. And you can clearly see that there's some really nice internal waves on the orders of about 45, 50 meters tall. And these waves were so intense coming into the canyon that sediment was kicked up off the bottom and mixed 50 to 60 meters up into the water column. And this is, to me, this is a really cool plot that really shows the sort of data and the resolution that you can expect when you use a Wirewalker. And so I really like these plots. And there's a ton of other stuff that I can kind of pick out if I zoom in and show things around. But I think I'll end with that because I probably have already spoken enough for being far in the afternoon for a lot of you guys. And so, you know, if there's any questions or you guys want to reach out later, contact me. I'm more than happy to chat in more detail and all that sort of stuff.
Thanks so much for that, Chris. I have some questions, but I think I'll open the floor to others first. Yeah, Daniel, go ahead.
Hi, thanks for the presentation. I love it. Can you just, in very simple terms, explain how it does the downward movement and how it unlocks, so it goes back up, and then relocks, so it goes back down without using any electricity?
The simplest way to explain it is you've seen the one-way pull mechanisms on a sailboat. You got the rope and you pull it through two little things.
Yes.
So the rope
Yes.
can go one way, but it doesn't go back the other way. It kind of gets
Yeah.
pinched. It's a very similar concept to that. And so the Wirewalker will essentially hold its mass, and the buoy goes up and brings the wire through it with it. And then when the wave goes by and the buoy falls, the down weight pulls the wire back down. And at that point, it's kind of like that little cam mechanism on the sailboat. It pinches the wire, and then it yanks the Wirewalker down into the water.
What's the technical term for these one-way?
That is a good question. We just
Okay.
call it a one-way cam.
Okay, and how do you switch, or how do you release it at the bottom and relock it at the top?
So it's all mechanically done. It actually impacts the bumper on the bottom.
Okay.
And there's a diamond drive and things like that in the Wirewalker that actually interacts. Like I said, it's 100% mechanical, and these are all things
And
that were
there's
designed.
another bumper at the top that it bumps into?
Yep. So it's like pushing a switch into
Mhm.
lock it and don't lock it.
Mhm.
Right.
And
Yeah.
you said it's about 0.5 meters a second going up.
Yeah.
And is down usually faster or slower? I understand down depends on the waves.
Yeah, so it does depend a little bit on the waves. On average, it's going to take longer going down than it does going up. In fact, if you have really big storm, something like that, it might be pretty equal going up and down. But for the most part, it'll go down slightly slower than it comes up. And the round trip, say you start at the top, you're going down and back up. In most conditions, it takes about it'll travel 10 meters of profiling depth per minute, which is a weird concept to think about because it goes down and back up, right? So if you're profiling to 100 meters, it'll usually do that every 10 minutes. Or if you're going to 200 meters, every 20 minutes.
So a return trip on 100 meters is 10 minutes?
About 10 minutes, yeah. And that scales, right? So if you're going to go to 500 meters, it takes about 50 minutes. So, but the cam mechanism was all designed at DMO. It's kind of our own thing. It's not an off-the-shelf type cam.
What's the longevity of these mechanisms? What's the longest you've had them out there? What do you expect?
So that data plot that I showed that was 370 days long, I only showed the picture of 9 days of it, but it was the same equipment being used, same wire, same Wirewalker, same everything for 370 days. And it got back and we thought the wire was going to be worn and need to be replaced, but it looked like it could totally be deployed again. So, I mean, we've seen 20,000 profiles on a wire, and the Wirewalker is still ready to go for other, more deployments. I would say the wire probably needs to be switched out more often than anything needs to be replaced on the Wirewalker itself.
Cool.
That's pretty typical for oceanographic wire anyway. Like it's pretty rare to be reusing oceanographic wire again and again on a deployment just because of it's jacketed wire rope to help with corrosion. But over time, you just get little nicks and bumps in the wire, and you'd want to replace the wire anyway, even on a standard mooring. So like that's pretty normal.
Yeah, I would say from our standpoint, like the longevity is there, and it could pretty much last as long as you want. It's more about the sensors because they obviously still need power. So you could be power limited with the sensors. You could also be biofouling limited with the sensors in time. As far as the Wirewalker goes, it basically self-cleans the wire with every profile. So on the wire and the profiling, it's essentially a non-issue. And then if you profile deeper than 100 meters, we usually don't see very much fouling at all anyways. And so if you can profile deeper, you kind of get natural biofouling and a longer deployment life that way as well.
When did you just start? Are you selling them or renting them? And when did you start?
The first prototype was actually built in about 2001 at Scripps. But in 2000, things happen pretty slowly at universities. And so it went through a number of iterations. And then finally around, I think it was 2010, they started talking about selling these outside to other universities and stuff. And so in 2015 is when DMO actually became a company. So we've been selling them full time at DMO since then. So they're commercially available now. And there's, I would say probably close to 200 in use now, something like that.
Any other questions? Oh, you go ahead, Ron.
Yeah, it's not exactly a question. I was going to make a remark. Thanks again, Chris, for the presentation. Always good to see like a lot of interesting ways of communicating how the system works, because it's a little bit odd when you think about like, oh, it's powered by ocean waves. But one of my favorite parts about it is just the way that the whole mooring is what moves and it stays put in the water, you know. But anyway, that's my own kind of my own appreciation of how the system works. It's wonderful. What I was going to say is, again, it's a remark. It's not really a question. It's just like there's so many plots you showed where there's periodic variation in the water column. And if you don't get that kind of resolution, you know, you could be potentially aliasing how the real conditions are changing and making a prediction on just completely wrong, you know, changes in the ocean. Like you maybe see it, like if you're using fixed sensors on a mooring and you see, well, there's this kind of slow variation, but you miss how rapidly things can change. You know, that's kind of an important consequence, and it's highlighted by the examples that you're showing in you know, in the plot. You know, nature's got lots of abrupt, harsh changes, and what are you going to do? I mean, it's really fascinating to see those differences. So yeah.
It's been really cool too that sensors in the last few years have gotten really good. So, you know, CTDs can sample like 16 hertz. You know, DO sensors are good enough now to work every second. You know, you can make a new measurement and they actually collect new data, not just blurring the data over, you know, quick samples or something like that. So sensors really help to get that resolution. But yeah, moving them through the water column, it's quite economical too, right? You're only using one sensor package. And so that's kind of what I like about it, is you spend less money on the whole thing.
Were all the sensors then they're recording internally and have their own internal batteries, or do they go to like a central main logging unit? Or
that's a great question. So right now, DMO doesn't provide any electronics. And I say right now because there's things happening in the background that hopefully will come out soon. But right now, we do rely on something like the CTD to act as a central data logger. And then we can put external batteries and things like that to increase endurance if you've got extra fluorometers and other sensors on there. There's quite a lot of space. In fact, we've put two 56 D cell batteries on Wirewalkers before, plus like the CTD and geosensor and fluorometer and all that sort of stuff. So the Wirewalker it's probably not as small as you might picture from some of the photos I shown. It is about 5 feet tall, or 1.6 meters or something like that, for people who speak in real units.
Majid's up next.
Yeah, thank you. Thank you, Chris, for great presentation. A question I have, what's the limitation of the wave frequency and the heights and the motion of the Wirewalker?
That is another great question. And I wish I had a good plot to show you. The problem is we haven't been able to get anybody's data that also has a really high resolution, like bottom mounted ADCP doing wave measurements. Because I can't look at like a wave buoy and say that there's a period cutoff here or a wave height even cutoff, because it doesn't get that resolution. So far, if you're looking at wave buoy data and there's something, it should work. In fact, the first picture, maybe I'll see if I can bring it up here again. Well, the first picture that I show, oh, it's gonna take me forever. Anyways, I'll try to talk while I do it. The first picture I showed was from Madeira Island off of Portugal, I believe. And it was a real actual deployment. There you go. This is a diver taking this photograph, looking up towards the surface. And so there's no bubbles on the surface at all. It was glassy calm, and there was about less than 10 centimeter waves. And granted, it went down pretty slowly. It kind of inched its way down, but it was moving, even in that super calm states. We've actually even seen it work in the Great Lakes and some smaller lakes here in kind of middle of California. If there's a little bit of wind chop, it starts moving.
And does the slope of your wire affect the motion as well?
It does. So you want to use a heavy enough down weight so that the wire stays pretty vertical. If you're moored and you're in very strong currents, let's try to use my hands for this one. Your mooring can tilt and get pulled and go taut. And now your Wirewalker is essentially a kite, and the currents are going to blow it up towards the surface. So it's going to have a really hard time going down. Plus the buoy's bouncing up and down less because it's also getting pulled. So that's, where something like Proteus DS or modeling it in a real state will help you say like, oh, I need heavier down weight, or I need a longer catenary, maybe I need a bigger buoy even. Some of these like 5,000 meter deep moorings that we've done recently, instead of using our small 275 kg buoy, we've put like a 700 kg pressure tolerant buoy as a surface buoy.
Good questions, Majid. Mine was kind of like, the only thing I could think of that sort of compares to it is, well, aside from going out and taking a profile yourself, is more like a winch and a profiling buoy. And I'm kind of wondering, what your thoughts are on a comparison between the Wirewalker and say a profiling buoy. I know Ocean Networks has one, so Matt might want to chime in here as well.
Yeah.
Ours is big and expensive and needs lots of maintenance.
Yeah. When you say expensive, what's the order of magnitude, do you think?
I think we bought it maybe 8 years ago. I think it was. We bought the system. There's probably not much change out of $1.5 million or something like that.
Okay.
2 million. If we count deployment and sensors, you're probably up to 2 million or something.
Okay, I gotta change our prices real quick. So like a super well like the buoy, like the picture from Hawaii, right? Something that had quite a few sensors like that, and the Wirewalker, it's most likely you're still looking under 200K. The Wirewalker itself falls into like the $50,000 range for the mechanical portion, and then whatever sensors are going to add to that. Obviously, that can range from 10 to 50 for whatever sensor. But yeah.
Okay. Yeah. Thanks. So kind of order of magnitude difference in cost, life cycle cost, and whatnot. So cool.
The buoys that pull things up in, I think it is cool, and it's a awesome way to get around biofouling when you're in like shallow water. I've always been a little bit concerned with if a storm comes by, how much that moves around and how safe the sensors are, or is there a chance of entanglement, anything like that. I haven't really seen any of them enough to say that's a viable concern or not. But what I do know is the Wirewalker would actually profile faster during that storm. You'd actually collect the more data when it's really interesting conditions.
Well, I have seen from my days at AML, instruments coming back, instruments that were allowed to freely move inside a well in an offshore buoy. And let's just say the instrument cage was extremely dented. But I will let Dan. Dan's got a question.
Yeah, I was just wondering what the process looks like for tuning the buoyancy, and obviously you want to look at you want that to be at the right rate for the sensors that you have on the unit, and also I imagine that would affect your sort of ratcheting down the speed that it would go down as well.
Yeah, if you over ballast it's got to fight the buoyancy to go down, right? So there's kind of a sweet spot, and what we found is that's about 0.4 to 0.5 meters per second. So it's very not similar to a glider where you're talking grams, right? We're talking about like a 2-inch thick little block of foam, and you're putting them in and out, you know, depending on oh, that was too fast. Okay, put one in. Okay, that's too slow, you know, whatever. So it's a pretty coarse ballasting procedure that usually you can get done in about an hour or two. What we like to do, the ideal conditions, I'll say this, ideal conditions would be if you have like a 10-meter tank. Secondary to that would be to go to a dock that you've got a few meters of depth, and you can actually just grab onto the wire and you can move it and simulate the waves yourself with, you know, maybe like a 10-pound dive weight at the bottom. And just by pulling up and down on the wire, you can make it go down. And by using your hand, you can actually feel on the wire when it hits the latch. And then you can start a timer and just like boop and watch it come up to the surface. So the trick there is that you don't want to do it in like 2 meters of water, because it needs to reach its terminal velocity to really estimate that. So I would say, you know, at least 6-7 meters of water. 10 meters is better.
Can you do that if you have like 3 or 4 systems that are set up the same? Can you do that once and sort of replicate that same setup?
Yeah, you know, if they're totally all set up the same, I think you're within error. You know, if one has an extra bolt or two, or somebody went crazy with the zip ties, you know, something like that, you're within that error for sure of one block of foam. We're playing with some other things right now as well. And so this next batch that we're shipping out soon, I hope to get them ballasted. We pre-ballast everyone. So they're kind of ballasted to like Scripps water. And so you should do your own testing when you get it, you know, because your density is going to be different. But we get it close. So you should only have to put 1 or 2 blocks in or take 1 or 2 blocks out. But the reason I say that is because as long as you're not changing the drag of the instrument going up, I think you can put pretty much anything you want on it, and we should be able to have like a, you know, positive buoyancy of 8 pounds, and you just kind of estimate that, put your 8 pounds of buoyancy in, hang an 8-pound weight from it, get it neutral, and then that should speed up the process a lot. But we haven't quite tested that for whatever reason, but we are working on it.
Thanks.
Ray's got a question.
Yeah, it's more of a comment. I do have to run out in a few minutes. I just wanted to thank you, Chris, for a very interesting talk. I think the mechanism is the most interesting thing to me. I'm not really into ocean sciences. I build things, and I can appreciate the beauty and the simplicity of this design. I think it's very robust, right? Because you're talking about thousands of cycles and no problems. So congratulations. I think you have a very, very innovative and simple device, and simple is not easy to achieve sometimes.
When you put moving parts in the ocean, it's not always the best decision, right? And so minimizing those, but keeping it simple, like you said, is a good way to go. So thank you. I appreciate it.
Awesome. All right, thanks. And with that,
I wish I was the one to take the action. You know, I'll pass it along to the smarter people that actually designed it.
Well, you have the intelligence to stay with it, because it's obviously working for you. So with that, I'll sign off. Thanks very much, Dustin, for setting this up. And it's nice seeing you guys, and we'll catch you next time.
Sounds good. See you, Ray.
Okay, bye-bye.
Bye, Ray.
Not sure if we have any other questions.
Maybe just a comment on that, on what's been just said. It's funny because when I read the description of this talk at first, when you were talking about like a wave power buoy, I thought it was like a powered by like a complex like wave energy converter. And I was thinking, oh, that thing must be like very complicated. And then it's definitely not. Right? It's funny.
Yeah, it's really as the salesperson for DMO, it's incredibly difficult to describe in few words. So if anybody has better ways or phrasing that would work well, let me know. I'm more than happy to take any suggestions.
Mooring zigs and the Wirewalker zags. I don't know.
Cool. Thanks a lot, Chris. That was super interesting, and I thought we got into some cool questions too. So maybe we'll cap it there, and just let everyone say bye, and maybe thank Chris for an awesome presentation.
No, thank you for letting me do it. And if anybody wants to contact me later or chat, has more questions, you have my email address. Feel free anytime.
Awesome.
Awesome. Thanks, Chris.
Great.
Bye, guys.
Thanks, Chris. Nice to meet you.
Bye,
Good to
guys.
see everybody.
Bye, guys.